Today we're going to talk about compositions of functions, and specifically the domains and ranges of some combinations of our families of functions that we've been dealing with all year long. So a quick reminder what a composition of functions means, and the way we write it, this f of g of x. It means we take the result of g of x, of the inside function, and plug it into f of x, the outside function. So we saw some of these examples earlier in the year, like if f of x, if one function is 2x plus 1, and another function is x squared, g of x is x squared. If we wanted to take f of g of x, that means take what was in g of x and plug it in as the input into f of x. So we could also write that as f of x squared. And that means taking x squared and plugging it in where the x is in f. So that's 2x squared plus 1. That's the main idea. It is really important to note that there's a difference between f of g of x and g of f of x. The order that you do the functions really does matter. For example, if we've got one function, a of x is sine of x, and b of x is x squared, the order that we compose those two functions really matters. If we do b of a of x, that means we are taking a of x and plugging it in for b, or in for x into b, which means we are taking b of the sine of x, means plugging sine of x in to x squared, which means we have the sine of x squared, which we don't usually write like that. We usually write it as sine squared of x, but they mean the same thing. Of course, a of b of x means something totally different. That means taking our b of x, taking our x squared, and plugging it into the function I've called a. Well, that's very different. That means we are taking this x squared and plugging it in for x, which means we would have the sine of x squared. These are two very different functions. The general idea behind compositions, and this is a diagram that I love to allude to, or refer back to, is this idea of a conveyor belt. A composition, generally speaking, a function means you take x, you plug it into some function, just call that f for now, and you get the result out. A composition means we take that result and instead of just ending there, we plug that result directly into another function. This one would be g of f of x. Because we took the result from f and plugged it straight into g. This idea of a conveyor belt is very helpful today. Okay, so let's get down to an example. We'll talk about the domain and range of a function and see how to figure it out. So again, here's just that same conveyor belt idea for f of g of x. So if there's a domain restriction on f of x, and notice how in this case f is the second one, g is the first one. If there's a domain restriction on f of x, it's almost like there is a gate here. It's like there's a bouncer carting at the door. You must be 21 or older to get in here. But what that means is we have to control what comes out of our first box, because it's got to get past that second gate. So I'm not going to put something into my first box, into my first function, whose result is not going to fit into my second function. Imagine if this was a factory and you had a machine that reshapes an object, and if you put an object in and it reshapes it into a shape that doesn't fit into the next box, well, then your whole factory is going to break down because you're going to have a logjam of things not fitting into the second box. We can't put something into the first box if its result won't fit into the second box. And that's the main idea, talking about the domain of a composition of functions. Figure out what is the gate, what is the requirement for getting into the second function, and control what we put into the first function in order to make sure we don't mess that up. So let's look at an example. Two functions, square root function and a sine function, two of our good old parent functions. It is really helpful if you continually think back to what parent functions look like. We know the parent function of a square root graph looks like that. we know the parent function of a sine curve looks like this. So just thinking of, and of course this keeps going also, keeping those parent functions in your brain is very, very helpful. We're going to be talking about f of g of x again, which means I will kind of label that up here. F of g of x means first the function goes into g of x, and then we take that and plug it into f of x. So the input that's going into f of x is the sine of x. But we've got a problem here. It's not really a problem, but we've just got a gate restriction here. We've got rules. You can't put anything you want into the square root of x. You can only put positive, or I should say 0 or greater in values into a square root of x. So that's the domain restriction of f of x. So what I want you to do is write this out as an inequality here. So we know that sine of x is what's going into the square root of x. But that thing that's going into the square root of x has got to be greater than or equal to 0. Because we can only put things that are bigger than or equal to 0 into a square root, and we're putting the sine of x into the square root. Well, that means the sine of x has to be bigger than or equal to 0. So what we do is then we work backwards to figure out, okay, so what must x be in order for the sine of x to be bigger than or equal to 0? And this is where thinking about the parent function helps. This is the parent function for sine of x. And we can see that sine of x is positive. It's greater than or equal to 0 here. Well, when is that? That's everything in between 0 and pi. Which means as long as x is between 0 and pi, sine of x will be positive, will be greater than or equal to 0. And then we can take its square root. Well, what we've just done is figured out the domain of our composition of functions. So I've meant to do this before, but writing out f of g of x, writing out this composition, keep in mind that we want to make sure we can write it as an expression like this. Also, the square root of the sine of x, because we are taking the sine of x and plugging it into a square root. Well, its domain, as we just found, is everything between 0 and pi. Now, you might be asking a question about, like, wait a minute, doesn't sine of x become positive again later? And you're right, that is true. It does happen again, and it happens again over here too. So you're right, it is periodic, so this will happen not just between 0 and pi. Really, it'll happen every multiple of 2 pi, or well, I'll say 0 plus 2 pi n to pi plus 2 pi n. But we'll just focus on this for now because it's a little bit easier, just between 0 and pi. So what we're going to do now is to find the range. What we do is take all those numbers, everything between 0 and pi, and actually plug them in. We are plugging them into the sine of x, and the question is, well, what do we get out? And there's a trick here. You've got to be careful, because it's very tempting to say, oh, well, when I plug in 0 to the sine, I get the sine of 0, which is just 0. And when I plug in pi, I get 0 again. So it's very tempting to say, oh, if I just plug these two numbers in, I get everything from 0 to 0. But no, that's not right. Because what we're looking at here is the range of the sine of x are all of the numbers on the y-axis that are the result of plugging numbers between 0 and pi into sine. And that set of y values, it hit a maximum in the middle of that interval, not at the edges. So it doesn't really matter to me that the sine of pi is equal to 0 again. What matters to me is somewhere in the middle, my y value, the range of sine of x, got as big as 1. So I plugged numbers between 0 and pi into sine, and I got out numbers between 0 and 1. And I take those numbers and I plug them into a square root graph. And this is where, again, it's very helpful to have that parent function in your mind. This is what the square root of x looks like. But if I'm only plugging in numbers between 0 and 1, because that was the numbers that came out of my sine graph, so those are the numbers that are going to go into my square root graph, well, I'm only going to get numbers between 0 and 1 on the y-axis. That's going to be my range. The resulting numbers are only the numbers in between 0 and 1. So what I've done here is I've taken the domain that we figured out earlier, plugged it into the sine to get sort of the middle step range, the range of sine of x, plugged those numbers into the square root to find out what the overall range is. So that means my range is only numbers between 0 and 1. I will never get a number bigger than 1, because even though if I take the square root of a bigger number, like the square root of 9, I could get 3. I'm never going to get a 9 to plug in. I can't get up to a 9 to plug in. The biggest I can get is 1, which means the biggest that's going to come out of the square root is also 1. And this will help a little bit after we see an example here. So this is a graph. I did it on the graphing calculator instead of on the Desmos because I wanted to point something out that's weird about the graphing calculator if you ever use it. Not that I recommend using it. But sometimes the graphing calculator is very glitchy. This curve, we just said that if you plug in pi into the sine of x, you get 0. And then when you take the square root of 0, you get 0 again. So you should be able to get all the way up to here. This is a bit of a glitch. The truth is that the graph really does go all the way to the x-axis there. Actually, there's a little bit glitchy on the other side too. Goes all the way to the x-axis there also. A little bit of a problem with the way the calculator does it. And so just remember what we've done. We want to make sure we scale the axes here. Those are all the x values between 0 and pi, and the result are all the y values between 0 and 1. Notice how it reaches my max over here, this coordinate right there. When x is pi over 2, we take its sine and we get out a 1, and we take that square root and we have a 1 again. But like I mentioned earlier, this isn't the only values you could plug in, because sine is periodic. Like we said before, if we try again, we get results there, we get more results there. So what's going to happen with our overall graph is, once we get past 2 pi, after I've gone through this gap where I've tried, if I plug numbers in between pi and 2 pi, I get into sine, I get a negative number, and then I can't take the square root. So they're not included in my graph. But once I get past 2 pi, my sines are positive again, which means that I can take the square roots of the result again, which means this little guy is going to repeat himself over and over and over again. I only have one copy, but it will keep happening out here too, and we'll just keep going. This is a periodic function. It will keep repeating itself. I do want to just show you something. You might be able to tell just by looking, like, that's not really the same shape as sine. It looks much more round, a little bit more like a parabola. But what we've seen throughout the last unit is that sine looks a little bit different. So here you can actually compare the two to each other. The orange line there is the sine curve, and you can see that the square root of the sine graph is a little bit different, because what happens when you take the sine of a number is you get a decimal. And the square root of a decimal is, believe it or not, a bigger decimal. So that's why in this whole area in here, after I've taken the square root, it's actually a bigger number. That's why it's always a little bit above the sine curve, except for when you take the square root, the sine of pi over 2, and you get 1, and the square root of 1 is exactly 1 also. So the two lines hit each other there. They're the same. But other than that, if you take the square root of a decimal, we get a bigger decimal. Think of an example for that is like if you take the square root of a quarter, or 0.25. Well, the number you have to multiply by itself to get to a quarter is a half, which is actually a bigger decimal than you started with. Okay. A quick summary of what we've done here, so you can kind of get used to this. And this is tricky. We'll see some more examples, but it'll take a while to get used to it. Quick summary is to find the domain of a composition, we need to start from the outside function, which is the last one on the conveyor belt. And we need to think, all right, what is the gate there? What are the restrictions, the domain restrictions for what can go into that last function? And then work your way backwards to say, all right, well then what is going into the first function? That's how we find the domain. To find the range, it's the other way around. We start at the end. Once we've figured out our domain, we actually plug it into the first box, see what comes out, plug that into the second function, see what comes out, and that's our overall range. When you do your Desmos activity, there are steps laid out. Like I ask you the questions that you need to be asking yourself, and hopefully you'll kind of train yourself to start asking them on your own. What I'll do is I'll give you an example, and I'll let you pause and try this on your own for a minute, and then we'll talk about it. So try and find the domain and range, and then kind of imagine what the graph of the sine of the square root of x will do. I'll give you a second to pause, and then we'll keep going. Okay, so we will find the domain and range. And again, it all comes down to imagining this conveyor belt. We're taking our inputs. We'll figure out what they are in a second. And what we're doing first to the input is the innermost function there is the square root of x. And then we're going to take the sine of that result. Notice how this is the same two parent functions, square root and sine, as we had in the last example. But the order that we do them is different, which is going to have a totally different result. Okay, this one's actually a little bit easier to find the domain because there are no domain restrictions on the sine of x. There's no gatekeeper there. There's no bouncer at the door telling me what can't get into the second door, so I don't care what comes out of the first box. Anything can come out of the square root of x, I don't care. Which means we just have to worry about the first gate, the first domain restriction. So since the domain of the sine of x, our second function, is all real numbers, we don't need to restrict the range of the square root of x, which means we only have to worry about what we normally can put into square root of x, which is, like we mentioned earlier, anything from 0 to infinity. So again, thinking about the parent functions is very helpful. We can plug whatever we want in here, and the result that we're going to get, if we take whatever we want and plug it into the square root of x, we're going to get out all the numbers from 0 to infinity. So that's what that blue line is. But then if we try and take that and plug it into the sine of x, again, notice how what we're plugging in to the second function, that blue line there, is the same as the range from the first function. But the numbers that we get out are everything between -1 and 1, just like any other time we do the sine function. So we're going to plug that in, and we're going to get out all the numbers between -1 and 1, and that is going to be our overall range. which sounds an awful lot like a regular sine curve. The only difference is we're only going to have numbers on the right-hand side of the y-axis because we can only plug them into the square root of x. So you might be imagining, oh, so it'll just look like this, like a regular sine curve, except not back here. But that's not quite what happens. There's one other little catch. And in order to think about what it'll look like before we look at it from the grapher, let's think about what the x-intercepts would be. The x-intercepts of a sine curve are at 0, and pi, and 2 pi, and 3 pi, and so on. But the numbers that are going into the sine, remember it's the square root of x, is going into the sine. Which means that the original x, first we take its square root, then we plug it into the sine. So these numbers here, the x-intercepts of the sine curve, those are really the square root of x. So the square root of x would equal 0, or the square root of x would equal pi, or the square root of x would equal 2 pi. These are the x-intercepts. So if I want to find the actual x values, sure, there's going to be one at 0, but the next one is not going to be at pi. The next one's going to be at pi squared. And the next one is going to be at 4 pi squared. And the next one after that is going to be at 9 pi squared. And what's interesting here is that the gap between 0 to pi squared and then pi squared to 4 pi squared, the gap is growing. They're not the same distance apart from each other. So let's take a look at how that looks on the graph here. And you can see that just like a sine curve, it's going to go up and down between -1 and 1. I'll put some labels here. -1 and 1. But the big difference here is it's going up and down in an uneven speed. It's going to take a lot longer to do that second round than the first round, because we got here from 0 to pi squared, but then the next one doesn't happen until 4 pi squared. And the next one after that doesn't happen until 9 pi squared. And after that, it'll be 16 pi squared. So those distances are growing and growing and growing. Worth pointing out that if we wanted to do this in degrees, we certainly could. It would look exactly the same. The only difference is what I just did a second ago to find the x-intercepts. The square root of x would equal 0. The x-intercept in degrees would be at 180 degrees. And then another one at 360 degrees. Well, when I start squaring those to find the actual x-intercepts, those would be very, very big numbers. 180 squared and 360 squared. We're talking about, tens and into the hundreds of thousands here. So that's why I'm not going to use degrees here, because this would have to be such a big number to make it work.